Welcome to the recovery section of the FDR. I'm Juno, I'm a third year Mechie, and I'm this year's recovery lead.
And my name is Michael. I'm a fifth year MAT student.
I'm Caitlin Riley. I'm a second year Mechie student.
So here's a quick table of contents. Our section is going to be structured the same as the previous sections. We'll just go over our design, the analysis that we've done, and then we'll go over our plans for the rest of the semester. So our most pressing self-imposed requirements for this year are that we're going to use a dual bay recovery system. This is just because compared to single bay methods, it tends to be more reliable. We're targeting a ground hit velocity of less than 8 meters per second, just to limit any chance that there's damage to the rocket when it hits the ground. And we're implementing fox hunting beacons as an alternate way to find the rocket after it lands to the trackers that are in the avionics bay. Some requirements that are imposed by Ezra on us are that we need to use a dual event layout, which is of course also covered by our choice to go with dual bay. Our drogue descent rate must be between 20 and 40 meters per second, and the main parachute must deploy at no higher than 1,500 feet AGL. And some requirements that were imposed on us by the other sub-teams are that for payload, we need to eject the payload at apogee since it's contained within the drogue bay, and the payload sabo needs to be integrated with the recovery harness. And for structures, we need to integrate the fox hunting beacons, or mounts for the fox hunting beacons with the bulkheads, and we need to just make sure all of the recovery hardware fits within the space allocated in each recovery bay. So, overview of our costs for this year. The total cost of the recovery bay is around $685. Most of that cost is taken up by the parachute, and then most of the rest of the cost of the recovery system this year is material for the recovery harnesses and for extending and repairing the streamer. I'll hand it off to Caitlin for our design choices.
So for design choices, our first thing that we're going to talk about is the lines diagram. On this slide, you can see the side of which side's going towards the booster and which one's towards the nose cone. As a general rule of thumb, your shock cord should be about 5 times the length of your rocket, and so that's what we tried to do here. Obviously, with our rocket being about 10 feet, we went with 50 feet shock cord that connects everything. One of the main things we also worried about was making sure the payload has enough shock cord to be away from the rocket, trying not to damage it in any way. And we also have bags for both the parachute and streamer to protect them coming out of the rocket. The next slide is our deployment phases. First, drogue happens, and that's when the streamer comes out, as well as the payload. And obviously the streamer just tries to slow the rocket down. And then main is the second event that happens, because obviously this year we're doing dual event recovery system. And then the main opens and slows it down to the correct speed. Another thing that we're doing differently this year is using soft links instead of quick links. Soft links are obviously lighter and less bulky, and with quick links you always have to worry about it damaging other components in the rocket. So soft links are just kind of an easier choice to go with. We also have had them donated to us, and they hold up to 6,480 pounds, which is significantly more than we're expecting them to take. Our parachute that we're going with this year is the IREC Ultra Standard. Has a coefficient of drag of 2.16 and a mass of 709 grams, and also has a pack length of about 7 inches long. We're also going with a drogue streamer, as previously mentioned. We are lengthening this from 110 feet to 100, or 250 feet. It is from last year's streamer that was made by last year's recovery team and has a calculated coefficient of drag of 0.05, which is based off the data from last year. It also has a packed length of about a foot and has a mass of a little over 1,500 grams.
Thank you. The shock cord we're planning on using this year is 3/8 inch in diameter. And the load rating, I believe it says, 4,600 pounds. The overall length of the shock cord is about 115 feet, and that's spread amongst the different deployment sections. And the overall pack length is about 5 inches, and again, that's separated by the different sections, so that's not the total length combined, it's all separated in different sections. In addition to the tracking hardware we're using in the avionics bay, we're also implementing fox hunt beacons to better locate the rocket. These beacons were used previous years, and they emit a radio signal that you can directly locate within about 2.5 miles. To locate these beacons, you use a directional antenna like the one you can see on the screen, where you survey across the landscape until you can get lock on the beacons. This again is used in addition to the other tracking systems implemented in the avionics bay. So in the event that other tracking systems fail, we can use this to locate the rocket, and then hopefully get lock on the other systems. To mount the beacons to the rocket, we're implementing 2 different beacon mounts. They are each affixed to bulkheads. The top beacon mount is implemented and integrated with the Clover bulkhead, and then the bottom one is mounted above the booster. These are both epoxied into place. They are 3D printed, and the beacons will be affixed into these mounts with zip ties. This is similar into design from previous years that successfully held the beacons in place. For the locations of the beacons, we're planning on implementing one on the top of the rocket, and that mounts onto the Clover bulkhead, and then the bottom beacon is mounted onto the booster bulkhead. In the event that the rocket disassembles into different parts, we should be able to locate each part individually using the beacons due to their locations. Next up is the charge wells. The charge wells we are planning on using are PVC end caps, and these will hold the black powder and igniters. These will be epoxied onto the avionics bulkheads.
So this year, the major risk that we've identified with our design this year is that we have a relatively low certainty about the drag coefficient of the streamer. This is because streamers in general are a little bit less understood than parachutes. So the current assumption is 0.05, and this is based off of flight data from last year. But since we're extending it, the current assumption might not hold up. So this is the biggest risk that we've identified. So moving on to our analysis, some risks that could occur during flight are that the payload tangles with the streamer or the drogue harness, and so what we've implemented to mitigate this possibility is that there's a static line on the drogue harness that's 20 feet long. It holds the deployment bag for the payload's parachute, so this will prevent the payload from deploying its parachute until it's a safe distance away from the rocket. It's also possible that either the main or drogue bay could fail to separate during flight. So the causes of this could be that the drogue charges are sized incorrectly, or that the shear pins that we use to hold the base together aren't consistent with the ones that we use during deployment testing. And that's a possibility just because shear pins in high-power rocketry tend to just be small nylon screws. So we will be having a primary and secondary charge in both the main and drogue bays, where the secondary charge is about 50% larger than the primary. So that, and this is so that if the primary fails to separate, the secondary charges should be able to separate the base. And we'll also be using the same like manufacturer shear pins for deployment testing as we will for the actual flight. So we shouldn't see too much inconsistency between how they perform in either case. And a smaller risk that we've identified, just because it's happened in the past, is that the drogue harness could be damaged or like severed by the lip of the body tube if deployment occurs after like a suboptimal flight. So we're not doing anything too extreme just because this is a low probability, but we are sticking with a shock cord that is a bit thicker than we necessarily need to for loads like the snatch forces. So we can get an idea of how far the rocket is going to be drifting using open rocket simulations. So in the table that's shown here, you can see a few different wind cases. These are all simulations that are run with the assumption that the wind velocity is constant and that the rocket is launched directly upwind. And just because of the amount of variability that there can be with the weather, our results in terms of our estimations of a landing point are quite sensitive to these conditions. And we're also assuming that the streamer's drag coefficient is 0.05, as I mentioned before. And this also has an effect on the landing spot, just because a higher or lower drag coefficient will change for how long the rocket's going to be in the air. So to get an idea of how sensitive to conditions these simulations are, here's an example of a Monte Carlo simulation where the wind speed and direction is varied. So in this like data set, the landing spot covers a range of around a square kilometer, so it is a very large area. But as we approach the launch day, we'll be refining our estimations of where the landing point will be using weather model data, as you have explained earlier. So for black powder charges, these are what we're using to separate the rocket. We have a primary and secondary in each bay. So in the main recovery bay, the primary charge will be 3 grams and the secondary will be 4.5. And in the drogue bay, the primary charge will be 4.5 grams and the secondary will be 6.8 grams. And they're sized to target internal pressures of 10 psi for the primary charges and 15 psi for the secondary charges. These calculations do assume that there isn't any friction between any body tubes or any of the components in the recovery bays, and that the force holding the rocket together is just the strength of the shear pins. So this would lead to an underestimate of the amount of black powder needed to separate the rocket. We're also making the assumption that the dimensions of the recovery bays just equate to the internal volume that's available, and this isn't true because there's, of course, the recovery hardware inside of the bays. So that could lead to an overestimate. So these numbers aren't necessarily set in stone. We'll have to verify them using deployment testing.
Thank you. You can see here the different forces acting on the recovery components. The largest force experienced will be on the parachute, and this is distributed against the shock cords. And then the other largest force is going to be from the streamer onto the shock cords as well. You can see the safety factors determined from these load cases. So the shock cord has a safety factor greater than 6, and the soft links also has a safety factor greater than 9. So we're not concerned with either of these components. And both the swivel links and eye bolts have a safety factor greater than 3. In terms of our mass budget, the heaviest components include the parachute and the drogue streamer. This is largely due to the extension and length that we're doing. And the overall mass budget equates to about 4.8 kilograms. For our power budget, our only component involving a battery are the beacons. The estimated battery life is about 29 hours. So we aren't very concerned with the battery life of the beacons as long as we adequately charge them prior to launch.
So for manufacturing, we want to get work on the streamer done and the beacon mounts finalized before March. Then once we have the beacon mounts and charge rails, we want to integrate those with the bulkheads before April. And then once all of our other manufacturing is done, we need to have the harnesses integrated with the rest of the rocket, given the rocket is complete, so that we can do deployment testing before the end of the semester. And we have some tests planned. Our first test is that we'd like to do a kind of a stress test with the payload saddle, since it's positioned right above the drogue charges, just to make sure that it won't be damaged during deployment. For the beacons, we're going to be doing more range tests, just to see if we can find kind of the maximum range that we can hear the beacons from. And we'll also try to get in some just fox hunting practice for all the members of the recovery team, so that we'll be ready to find it in the field. Then for the harnesses themselves, we'll be doing pull testing just to make sure there's no catching or tangling during deployment, and then we'll have full deployment testing once the entire rocket is ready. So just a few risks to getting all those items done on time are that some members of the team, including myself, are on co-op, so we're not always in the area to be able to work, and we're also relying on sewing machines in the shed to be able to work on the streamer. So if those machines were to be down on the times that we're planning to work on the streamer, that would set us back. But those are our main risks.